Okay, so when Cauchy begins working, at that point, and really almost from the very beginning, integration had been linked fundamentally with anti-differentiation. So even though it had first, in some sense, been conceived of as the area under the curve, remember Leibniz talked about splitting up the domain into a bunch of small pieces and computing the areas of these rectangles, and he came up with these difference formulas and things like that. So even though in some sense, and Newton did as well, by the way, not that exact thing, but he came up with areas under the curve. Even though that is kind of how integration started, it soon became the idea, or the idea that the guiding paradigm just became that integration was simply anti-differentiation. So if you had a differential form, the integral of that differential form, and when I say differential form, I just mean something like f of x times dx. The integral of that differential form was just the function whose differential was equal to that. So, for example, if you wanted to integrate something like f of x dx, then the answer here is just going to be the antiderivative. That is the function f such that df is equal to f of x dx. In other words, just the anti-differentiation, the antiderivative of little f. This started to become a problem and not ideal for a couple of reasons. It's not the more fundamental thing. The more fundamental thing is area under curves or some sort of notion like that in terms of sums. So something like that. There's various different ways that it can be defined or it can be interpreted, but that's one of them. And that's sort of the more fundamental thing. But really, the issue with stuff like this is, what about functions like e to the x squared or cosine of x squared? These are not functions that had elementary antiderivatives. And of course, once you start thinking about things like this, there's other things as well that don't have elementary antiderivatives. So if you want to compute something like this, there was typically always some sequence or some interval here in mind, but I'll get rid of that for now just to be a little more clear. So if you want to compute the integral of some function that does not have an antiderivative that can be expressed in terms of elementary functions, well, what do? Well, the answer is that if you want to compute it, you compute it using some sort of numerical method, some sort of approximation. And you learn all of these approximations when you're taking your calculus class. Just the normal rectangle approximation. You could do Simpson's rule, trapezoid rule, whatever, different ways to do this approximation. Okay. Now, what Cauchy does is he takes that idea of the approximation and he turns that into the definition of integration. Okay, he takes the approximation, he takes what was being used just as an approximation, and he says, let's define this approximation. Of course, in a certain appropriate limiting sense, let's apply this, let's take this approximation and then define an integral to be equal to the limit of these approximations. And I'll get to that in just a little bit, but before I do that, I want to mention another sort of uniform property. So in the video, in the last video I mentioned uniform convergence. Now I want to mention uniform continuity. So I think either in the last video or the one before it, I mentioned that Cauchy is the one who sort of gives us the more modern definition of continuity. Weierstrass gives us an epsilon delta thing. Cauchy gives us an epsilon delta thing, but not stated that way, just kind of stated in words. But one thing that he does is he defines a function not continuous at a point, but continuous on an interval. And I think this is probably one of the reasons that he sort of thought a little bit differently when he was giving this wrong proof for this theorem, quote unquote theorem, about the convergence of a sequence of continuous functions. He said he was kind of thinking in too uniform of a sense. So a function, let me say it this way. Do I have enough room here? A function f is, and I'm going to write u continuous for, no, I can do just a uniformly continuous. I can write it all. uniformly continuous on an interval, and we can make it a more general set, on an interval I, if for all epsilon greater than 0, there exists a delta greater than 0, such that f of x minus f of y is less than epsilon whenever the absolute value of x minus y is less than delta. Okay, and the important thing here is that delta only depends on epsilon. It does not depend on x or y. Only depends on delta. It does not depend on x or y. Okay, so in other words, if you know x and y, any x and y in the interval are within delta of each other, you know f of x minus f of y, the absolute value of x minus f of y is going to be less than epsilon. In other words, if x and y are close to each other, it doesn't matter which x and y, then we know f of x and f of y are going to be close to each other. Okay, now a fact that hopefully you learned at some point in your undergraduate education, in a sort of like basic sort of analysis class on the real line. So if you did your undergrad here, this would be like Math 409. Hopefully you learned a fact like the following. If f is continuous on a closed interval a to b, then it is uniformly continuous. If a continuous function on a closed and bounded interval is uniformly continuous on that interval. Okay, so it's a way of upgrading the property of continuity to uniform continuity. So once again, a function, if f is continuous on a closed interval, a closed and bounded interval, then it is also uniformly continuous on that interval. Now remember, Cauchy defined continuity to be over a whole interval. So he didn't talk about whether it's over a closed or he didn't explicitly make a distinction on whether he was talking about a closed interval or not. But I think reading what he wrote and reading what other people have said about what he wrote, it seems that this is what he has in mind. So he has in mind a continuous function on a closed and bounded interval, and because of things that were developed after that, we know that it is therefore going to be uniformly continuous on a closed and bounded interval. And so keep that in mind as I talk about Cauchy's, that's going to be very important as we talk about Cauchy's definition of an integral. Okay. So now what we're going to do is look at his idea of an integral. So I have his notion of an integral stated here in a little more generality than I'm going to talk about it here. So I want to think about the integral of a function just defined on 0 to 1, just the interval 0 to 1, and then you can make the adjustments if you want and think through how this is going to change if we look at an arbitrary an arbitrary left endpoint and an arbitrary right endpoint. Anyways, so we have some function that looks something like this. Now Cauchy does exactly how you learned about Riemann sums in your calculus class. At least I would imagine this is how you learned about Riemann sums. But as we will see, the sums that we typically call Riemann sums should probably really be called Cauchy sums. But it doesn't matter because as we'll talk about Riemann in just a minute. So what Cauchy is going to do is he's going to break the interval 0 to 1. I'm just going to say 0 to 1 and not a to b. He's going to break the interval 0 to 1 into evenly spaced intervals like this. So I'm going to call this point x1, x0. This is x1. This is x2. And this will be x sub n. There's going to be, in general, n points. So this is x sub n. In this case, it's going to be x3. So x0 is the left endpoint. X sub n is going to be the right endpoint. and then there are 0, 1, 2, 3, and whatever n is, that's the number of intervals there's going to be. And the width of each interval, I'm just going to call it delta x, is of course going to be 1 minus 0 divided by n. So it's going to be 1 divided by n, or in this case 1/3. So each one of these intervals has length 1/3. Okay, and he's going to develop an approximation to the integral with this partition. So I'm going to say that the integral is equal to I, and he's going to say that the integral I is approximately equal to the sum k equals 0 to n minus 1 f of 0 plus k delta x times delta x. Okay, or it's a little bit easier if we just call it f of xk delta x. Okay, so in this case, this is going to be f of x naught delta x. So it's going to be, we're going to be looking at the area of that rectangle plus f of x1 delta x. So now we're going to be looking at the area of this rectangle, and then plus f of x2 delta x. And so now we're going to be looking at the area of this rectangle like that. Okay, so this again is very familiar to those who have taken calculus, which I would really hope is everybody who is taking this class. Okay, so, all right, so he says, given a partition like this, so he calls this x0, x1, x2, xn, he calls this a partition of the interval. I'm going to redraw my function here, or redraw the graph of the function, I should say. Doesn't really matter, it's going to look different. Okay, so we have something like this. And in fact, let me make it change a little more. So something like this. Okay, for every partition with evenly spaced points like this, for every partition with evenly spaced points, we'll call this S. We're going to get some sort of sum like this. K equals 0 to n, n minus 1. F of xk delta x. Now, the evenly spaced part is not that important, but we'll see issues that arise. Okay, so now what he wants to do is he says, okay, so we have this. What I want to do is I want to refine this partition. In other words, in each one of these points, in each one of these intervals, I want to maybe bisect that interval. And so I'm going to have something here, 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 like this. Okay, for the sake of argument, this point is x naught. I'm going to call this new interval point here. I'm going to call this x naught prime. This is x1. I'm going to call this new one x1 prime. This is x2. I'm going to call this new one x2 prime. Okay, and now for this refined partition, which I'm going to call S prime. Let me actually write this out a little more explicitly. S, I'm going to call it S sub n because there are endpoints, is equal to f of x naught delta x plus f of x1 delta x plus f of x2 delta x. Okay, now what is S prime going to be? Okay, again, I'm using evenly spaced points, but I want you to modify this for the case that we're not using evenly spaced points. You can see kind of what one way to do this in the slide here, where instead of looking at, I think you can see this, instead of looking at delta x here, I'm actually not sure what the cursor is pointing at here. Instead of looking at delta x here, this is just xk minus 1. If you have evenly spaced points, these are all going to be equal to each other. Anyways, so see how to change this argument for the case of non-evenly spaced points. Okay, so now what we're going to have, so what is S prime going to be equal to? Well, S prime is going to be equal to f of x naught, and now it's going to be this interval here, 0 to x naught prime, which is delta x over 2. Okay, then we're going to have plus f of x naught prime times delta x over 2. Then we're going to have plus f of x1 delta x over 2. Maybe I have room to write them all out. Then we're going to have plus f of x1 prime delta x over 2 plus f of x2 delta x over 2 plus f of x2 prime delta x over 2. So this is S in, and well, you know what? I called this prime. I'm going to call it S sub 2 in for doubling. Okay. I've got S in. This is S2 in, and again, I'm thinking about S in as having evenly spaced points, and S2 in, we're just taking each interval and bisecting it. So now we have 2 in subintervals that are evenly spaced, and the lengths of these intervals are half the lengths of these intervals. Okay, now let's see if I can do something without having to completely erase everything else. So f of x naught prime. Okay, what is f of x naught prime? I'm going to change this in blue. I'm going to write this in blue, if I can find my blue marker. Oh, it's right in front of me. Okay, so f of x naught prime. Okay, well, let's think about this. It's just, we're thinking about f as being continuous. So f of x naught prime is simply going to be f of x naught plus epsilon naught, where epsilon naught is by definition the difference between f of x naught prime and f of x naught. And then we're going to multiply this by delta x over 2. And we're going to have similar things for f of x1 prime. What is f of x1 prime? Well, f of x1 prime is simply f of x1 plus epsilon 1. Or again, epsilon 1, by definition, is just the difference between f of x1 and f of x1 prime. And I forgot to multiply this by delta x over 2. Okay, now similarly down here, this is going to be f of x2 plus epsilon 2 delta x over 2. Okay, let me look to see if that's still showing up somewhat okay. Okay, this is an x here. This right here is x2. Okay, so I'm going to erase this and rewrite a lot of things, but here's what I want to point out. F of x naught times delta x over 2 plus f of x naught times delta x over 2. This, if you just look at these two terms right here, this is equal to f of x naught delta x plus epsilon naught delta x over 2. And we can replace all of these. So for this term, we're going to, if you look at, let's see, this purple term plus that blue term, you're going to get f of x1 times delta x times epsilon 1 delta x over 2. And then for these two terms, it's going to be f of x2 times delta x plus epsilon 2 times delta x over 2. So in other words, this entire sum, S2n, this entire sum, S2n, is equal to Sn plus epsilon 0. Let me write it properly. Or not properly, but just explicitly. Epsilon 0 times delta x over 2 plus epsilon 1 times delta x over 2 plus epsilon 2 times delta x over 2. Okay, now what do we know about epsilon 0, epsilon 1, and epsilon 2? Well, here's where we're going to use the fact that f is uniformly continuous. We're going to use the fact that f is uniformly continuous. And if we pick an epsilon greater than 0, any epsilon greater than 0, we can choose n so large, so that delta x is so small, so that the difference between f of x naught and f of x naught prime, that is epsilon naught, that's less than epsilon. And by uniform continuity means the difference between f of x1 and f of x1 prime is also going to be less than epsilon, and so on and so forth. If n is picked large enough so that delta x is small enough so that f of x minus f of y is going to be less than epsilon if x and y are within delta of each other. And of course, I'm only illustrating this with n is equal to 3, but think about n as being very big. We can make n as big as we want. I'm just illustrating it with n is equal to 3. So now what this tells us is S2n, if I look at the absolute value of S2n minus Sn, I'm just left with this part right here. It's going to be less than or equal to epsilon plus epsilon plus epsilon, because each of these epsilon naught, epsilon 1, epsilon 2 is all going to be less than epsilon. So this is going to be less than or equal to, and there are n of them. N is equal, there are n different things. N is equal to 3, but there's n of them. It's going to be n times epsilon times delta x over 2. But remember that delta x is just equal to the length of the interval, which is, in this case, is 1 divided by n. So this becomes epsilon divided by 2. Okay, so if we choose n so large that delta x, which is 1 divided by n, or the length of the interval divided by n, is so small such that f of x minus f of y is less than epsilon, when x minus y is less than epsilon, or less than delta, then we're going to see that each time we do a partition like this, the difference is going to be less than epsilon over 2. Now epsilon is arbitrary, so I can just, what this says is that eventually, we could by refining these partitions, if I have a continuous function and I start with one partition and I refine it this way more and more and more, eventually, if f is continuous, that is, if f is continuous on the closed interval, or if f is uniformly continuous on this interval, as we refine the partition, that is, if we add points more and more and more, that these sums right here are gradually going to go to each other. And then we say that there's one other step we have to make. This says what I've just argued is that if you start with a partition of evenly spaced points, and then you subdivide those, that and f is continuous, that s sub n approaches some fixed value s. That's what this argument shows here. That as we refine the partition, they come closer and closer to each other. Now, a refinement of that argument will show that you don't have to have evenly spaced points, but the argument itself still says if you start with a partition and then refine that partition by adding 1 point within every subinterval, that argument, basically the same argument that I did here, is going to show you something similar. That each time you refine, that is, each time you double the number of partitions you have, you're going to get a different. You will get a different sum, but that those sums will converge. But this starts with a certain partition, and now it starts with a partition, and you're refining this partition in a very particular way, where you are adding exactly 1 point within each partition. Okay, but there are going to be, if you start with some partition, there are going to be many partitions that are not reachable from that original partition via this algorithm. So for example, we're starting here with 3 intervals. So each time we double it, we're going to have 3. We double it, we're going to have 6. We double it, we're going to have 12. So there's no way to have a partition with 15 intervals. So you have to modify the argument a little bit and say, okay, well, if you have 2 partitions, you want to compare them, you can find a partition that is a common partition of both of them and apply a similar argument. And I'll let you think through how exactly that's going to work. Now, this is a key point that we'll come to in just a moment. This idea that for a continuous function, it doesn't matter what sequence of partitions you look at. If you have a continuous function and you start with one sequence of partitions, you're always going to converge to a number, and you're going to do that with any partition that you start with, or in any starting partition. If f is continuous, you're always going to converge to the same number, and that is what we call the integral of the function. But there's actually a problem here, and it's a problem that Riemann notices. So Riemann notices a couple of issues. Let me hold on. Okay, the title of this slide is Riemann integration. He notices a couple of issues. So to begin with, what if the function is discontinuous? Okay, well, Cauchy figured out what to do if the function is discontinuous at a finite number of points. You just break the interval up at these points where f is discontinuous. Okay, but what about functions that are not continuous and have an infinite number of points of discontinuities? What do you do then? What about functions that it seems like you could apply this algorithm, this procedure that Cauchy has given us, or that he's using, and you can take some partitions, and you'll take some sequence of partitions where the intervals get smaller and smaller and smaller, and you go to one value, but you can take other partitions and you'll go to another value. Okay, so what do I mean by that? So let's look at an example of something where you can apply Cauchy's construction and kind of get the value of the integral being two different things. Now, of course, f can't be continuous because what I just said, every time you have a continuous function that's uniformly continuous, Cauchy's argument is going to work. Or Cauchy's algorithm or plan or whatever, his definition is going to give you a consistent number that we can call the integral of this function. Okay, so let's look at this. What about if f of x is equal to 1 when x is a rational number and it's equal to 0 otherwise. So it's equal to 1 when x is a rational number. Now, if we do this using Cauchy's definition, and we use a partition of the interval that has rational endpoints, all of our f of x k's are going to be 1. And so therefore, whatever sum, all of the s n's, so if rational endpoints, all of the sums, s sub n, are always going to be equal to 1. If irrational, if the endpoints are irrational, then all of the sums are going to be equal to 0. And so now we don't have this thing where we've got finer and finer partitions, and they're all leading to the same value, because here we get finer and finer partitions, they're all going to be 1, and here we get finer and finer partitions, they're all going to be equal to 0. So what's the deal here? Is it just that f is not integrable? Do we need to change things? What do we do? And the answer is not as simple as it's just not integrable. Under Cauchy's definition, I would say maybe it's not integrable. I think that would be a reasonable thing to say. But on the other hand, and under Riemann's definition, it's definitely not integrable. But Riemann's definition of integral is one generalization of Cauchy's definition of integral. But there are other generalizations of Cauchy's definition of integral in which this function is integrable. So it's this shows, in my opinion, and other things show, that even though Cauchy got us really far to what the definition of an integral should be, there are still definitely questions, and the definition needs to be modified just a little bit. And there's going to be similar issues with Riemann's definition of integration as well that's not modified until the beginning of the 20th century with people like Lebesgue. Okay, so what does Riemann do? So Riemann does something a little bit differently. So if you think back to the key thing that was needed for Cauchy's definition, we needed to know something like f of xk minus f of xk prime could be made less than epsilon, and so, like this would work for all values for all of the k's. In other words, what we needed to do is we needed to show, we needed to have it be true that as delta x goes to 0, or equivalently as n goes to infinity, but we want to talk about for just a minute as delta x goes to 0, that the total difference of f, that is the biggest value minus the smallest value of f on each one of these subintervals goes to 0. They can be made less than epsilon. Okay, so here's what Riemann did. We need to introduce a few more ideas. So a partition P, again, this is exactly what we saw, is going to be a sequence of numbers x0, x1, all the way up to x n minus 1 and x in, and typically x naught is like the left endpoint, and x in is the right endpoint of the interval that we're working with, so a to b, and we're going to define a measure. It's called the mesh size of P. Is going to be equal to the maximum length of these subintervals. So the maximum of x1 minus x0, x2 minus x1, and so on and so forth. So it's going to be the max of xk minus xk minus 1. Okay, just the biggest subinterval that we have in this partition. Okay, so for each partition, Riemann is basically going to introduce two ideas, an upper sum, and there are various people doing similar things here. So this is really something that's more attributable to a mathematician named Darboux. So U of Fp is going to be equal to the sum k equals 0 to n f of xk. I'm going to put a star in the superscript here, times xk plus 1 minus xk. Sorry, this should be to n minus 1. Okay, so xk star is going to be the point in the interval xk to xk plus 1 where f attains its maximum. Now, for a moment, forget about whether or not f can attain its maximum on that interval, because remember, we're not dealing with continuous functions anymore. That's a good question that you have, but just forget about that for a minute. Or just, I'm not going to talk about that, but I don't want to get too far afield here. So f of xk star is something like the biggest value that f takes on the interval xk to xk plus 1. And then we're going to look at the lower sum. L of fp is going to be the sum k equals 0 to n minus 1 f of xk star. Now I'm going to put the star down here in the subscript, xk plus 1 minus f of xk, something like this. Now, we are assuming that f is bounded on the interval a to b. That is one of the things that we're assuming. And so, again, f of xk lower star is the lowest value that f takes on the interval xk to xk plus 1. And I now realize that this is going off of the screen. Instead of rewriting things, let me just, oh, that makes it worse. Let me just angle things differently. There we go. Okay, so now right what that says, I'm going to move it back now. Okay. Now, what Riemann says, so we have this very last line here, this omega of f comma ik times the absolute value of ik. So if we take the difference of these two, what we're going to get is the following. What we're going to get is the following. We're going to get u minus L is equal to the sum k equals 0 to n minus 1 f of xk star minus f of xk lower star times xk plus 1 minus xk. Okay, it looks like that is fitting on the screen. Okay, now this quantity that Riemann has, the sum k equals 0 to n minus 1, omega of f, comma ik, times the absolute value of ik. This is one measurement of the variation of f over an interval. Omega of f of xk, omega of f comma ik, we're looking at the kth interval, that is the interval from xk to xk plus 1. This quantity right here is simply the biggest value of f takes on an interval minus the smallest value that f takes on that interval. Now again, we're not assuming that f is continuous. So the largest value that f takes on the subinterval and the smallest value of f that f takes on the subinterval doesn't strictly make sense in this case. It might not attain its maximum. All we do then is instead of f of x k star and f of x k lower star, this we replace with the supremum of f over the subinterval, and this we replace with the infimum of f over the subinterval. Okay, anyways, I will again let you guys think through how to change that. So what Riemann says is that if this goes to 0, that is, if we can make this less than epsilon for all partitions whose partition size is less than some delta, that if and only if that's true, then the function is going to be Riemann integrable. Because again, remember what we needed to have happen with Cauchy. We needed these two quantities to be bounded absolutely for all values of k. And what Riemann introduces, he says, okay, well that's actually what I'm going to take as a definition. So continuous functions will always satisfy this, but there are discontinuous functions that satisfy this as well. And what Riemann says also, if a function is continuous, then it's going to satisfy this as well. If a function is integrable, it's going to satisfy this as well. So if a function does not satisfy this, then it's not integrable. And so if, for example, you look at the function that I put where f of x is equal to 1 when x is rational, and f of x is equal to 0 when x is irrational, this right here, this variation is always going to be 1, because for any interval, there's rational and irrational numbers. And so the difference between the supremum of f and the infimum of f, or in this case, indeed, the maximum value that f takes on that interval, and the minimum value is always going to be 1. So this is always going to be 1. We're adding up the lengths of ik, but this is a partition. So overall, this, for that function that I mentioned, is just going to be the length of the interval. In other words, it's not going to be less than epsilon. And so what this shows is that function that I wrote before, which is doesn't seem to be Cauchy integrable, is definitely not Riemann integrable. Okay, but again, like I said, if you want to take other classes, if you want to take graduate classes, you can actually find out that it is integrable if you have a different definition of integration called Lebesgue integration. Another thing that I want to mention is there is a modification of Riemann integration under which that function that I gave is also integrable. There is a mathematician from the 60s, I think, named Robert Bartle. You might have used his analysis book for your undergraduate class. He has one called The Elements of Real Analysis. I know because I'm looking at it on my bookshelf right now. He doesn't talk about it there, but he has a paper that I think might be in the MAA Monthly where he talks about this. This is from a long time ago, where you can actually modify the Riemann integration, the Riemann integral definition just a little bit to be able to integrate that function that I talked about before. But the point that what Riemann has done here is he has now introduced a larger class of functions that can be integrable. And not only that, he sort of expanded Cauchy's idea so that Cauchy's thing only applied to continuous functions or functions that were discontinuous at a finite number of points. And then if it wasn't continuous, it's unclear what Cauchy's definition would lead to. It would either lead to contradictions or something like that, and Riemann cleaned that up. And that's the definition that we really work with a lot today. And like I said, in fact, if you take like an undergraduate analysis class for us, that'll be 409. We concentrate a lot on the Riemann-Darboux integral. And there's slight differences, and each time I teach 409, I have to remind myself what those differences are. Okay, so finally, we want to talk about the fundamentals of arithmetic. Now, what I mean by that is just basically the fundamentals of the real number system. And I'm not even going to scratch the surface here. So, for a long time, it was known that in some sense there are more numbers than just irrational numbers. Okay, there's more numbers than irrational numbers. We talked about in the beginning of class how, at least by the time of the Pythagoreans, and probably before that, it was known that there is no rational number whose square is equal to 2. In other words, the square root of 2 is not an irrational number. Now, geometrically, okay, this is fine because if we think about a line going from here to there, from point A to point B, we can assume that it is going through all of the points in between, and if you have a square of side length 1, then the diagonal has side length, the diagonal has length square root of 2. And so from a geometric point of view, we can kind of see why irrational numbers, there's no problem. If you think purely in terms of geometry, though maybe even if we think about that a little bit, we'll have some doubt. But what about doing all of this stuff with calculus? We're not really looking at geometric pictures anymore. We're doing things with functions and differences. We're adding and subtracting. We're saying things like calculus was using concepts of continuity, not just continuous functions, but like magnitudes that change continuously, like x, the independent variable x moving from x to a, like in a limit. The limit as x approaches a of f of x. Well, what are we talking about? The x approaching a. We're approaching x is approaching a continuously. But what exactly does that mean? As x goes from 0 up to a, or from 1 down to a, or whatever the things are, we wanted to pass through all of those numbers. But what are those numbers that it's passing through? So we need to, Dedekind realized, okay, hold on a second, we need to come up with a way, and other people as well, we need to come up with a way of describing these numbers that are not rational numbers. Okay, because there are definitely more numbers than rational numbers. It seems like they should just be like in between the rational numbers and fill in the holes, but there's also a bunch of other stuff that had been happening that sort of gave them pause and were like, well, we need to really get this more foundational. So for example, the example the book gives is Weierstrass comes up with a function. You can look at this up. It's the Weierstrass M function or something. Or no, you I don't know what it's called. You use something called the Weierstrass M test to prove that this function is continuous. It's an example of a function that is continuous everywhere but differentiable nowhere. Okay, so like if you zoom in, what this means is whatever point you pick and you zoom in, it's never going to look like a straight line. That's what it means for a function to be differentiable graphically. If you pick a point and look at it under a microscope, if you look closer and closer and closer, or zoom in on Desmos, it's going to look more and more like a straight line. But Weierstrass comes up with a function such that when you zoom in, it just looks more and more ragged. It doesn't look like a straight line. And this is true for any point. So it's continuous everywhere, but differentiable nowhere. This is one of the things that kind of made people doubt some fundamental stuff. Okay, so what Dedekind does is he realizes the following. He says if you pick a rational number, you can split the all of the rational numbers, or all of the real number line, if you kind of want to assume something like that exists, into numbers that are to the into that. You can you can pick any rational number and split that between numbers that are less than the rational number and numbers that are more than the rational number. Okay, sorry. The screen, it's a little confusing because the video screen that I look at is not mirrored, but I'm expecting it to be mirrored because I'm looking at it, which now I realize is why the Zoom screen is mirrored. It's a little, the fact that it's not mirrored is a little bit disorienting. So anyways, if you have a rational number Q, this splits the rational numbers into two sets, A1 and A2. Every number in A1 is less than every number in A2, and you have this number Q that's not in either set, or you can arbitrarily define it to one of the sets. And it is the only number that has that property. It's the only number that is in between both of these sets. Okay, so certainly, excuse me, what we can do is for any rational number, we can do this. It doesn't matter what the rational number is, we can do this. But now we can define this idea of cuts. So a cut is going to be a partition of the real number line into two sets, A1 and A2, such that every number in A1 is less than every number in A2, and there's this one number that's in between A1 and A2. There's only one number that does not have this property. Now, it's clear that every rational number produces a cut, but there are some rational numbers there are some cuts that are not produced by a rational number. Okay, so for example, if we think about all of the rational numbers whose square is less than 2, let's call that A1, and all of the rational numbers, or all of the numbers whose square is greater than 2. In other words, using how we would think about it is that we are making a cut at the square root of 2. Okay, but the square root of 2 isn't rational. Okay, but if we say it without assuming the existence of the square root of 2, we can say something like all of the numbers whose square is less than 2, that's A1. All the numbers whose square is greater than 2, that's A2. Okay, now for numbers like this, maybe you think, well, do we really need to do this? Because, we just say, well, the square root of 2, we can define that kind of algebraically. We don't have to do it this way. We don't have to do it in terms of cuts. Square root of 2 is simply solutions to the equation x squared minus 2 is equal to 0. The positive solution to x squared minus 2 is equal to 0. And indeed, we could say any number, any number that is a solution to a polynomial with rational coefficients, that's just going to be, we can construct these numbers, these irrational numbers that way. But in fact, there's more rational numbers. There's more irrational numbers than just these. What about if we look at A1 is all of the numbers that are less than the area of a circle of radius 1. And A2 are all of the numbers that are bigger than the area of a circle of radius 1. So A1, all numbers that are less than the area of a circle of radius 1. A2, all of the numbers who are bigger than the area of a circle of radius 1. Well, what's the area of a circle of radius 1? It's pi. Well, we know that pi is a transcendental number, meaning it's not the root of any polynomial with rational coefficients. Okay, so in this way, what Dedekind does, you have a new cut. Okay, you're able to do a cut, and it's not a rational number that's the cut. He says, okay, well, this is like a new creation of the mind. He's like, this number here that is missing, it's not a rational number, it's a new creation of the mind. This is a cut, and that's what the irrational numbers are. Now, other people said the cut itself should be called the irrational number, and now all numbers are just going to be defined as cuts, stuff like that. But doing this, Dedekind was able to sort of fill in the holes, quote unquote, in between the irrational numbers. Now, this was step 1. There's still a whole bunch of other steps, because you can define. We made that definition. The definition isn't so difficult. We said it pretty precisely, so there's no issue there. The issue now is, how do you define, with this idea of cuts, how do you define all of the typical operations that you want to do to numbers? What does it mean to add 2 cuts together, subtract 2 cuts together, or subtract 1 cut from another, multiply 2 cuts, take the square root of a cut? Is it true that if you do a cut times a cut squared is equal to a cut squared times a cut squared? So all of these things that you have to answer. Now, I'll let you read about this in the book. It's a huge area, lots of things going on there, but I think that's where I'm going to end this video. Anyways, okay, so this will be my last video, I think, for this week. I don't think I'm going to make any more. And like I said, this is sort of coming to the end of sort of a calculus and analysis type of thing. As we will see, we're going to look at more algebra coming up. But even a lot of the stuff that we've been doing so far is not purely calculus and analysis. Indeed, there's all sorts of algebraic things going on with differentials and stuff like that. Some of these things we might get into in the coming